Hi, this is the Spring 2023 exam number 2 for MA 166. So starting with problem 1 asks, compute the integral of sine x to the power of 5 halves times cosine x cubed. Alright, so this is obviously not an expression that we can use one of our basic antiderivative rules for, so we need to figure out which integration technique we can use to integrate this. Okay, so in this case, the integration technique we want to use is u sub. So we want to use u sub. And u substitution is when we essentially do a change of variable on our expression. We set u equal to, in this case, we can set it equal to sine of x, and then that would make du equal cosine x. And so why this is like a good choice in this case, why u sub is a good choice, is because we have both sine and cosine in our expression. And since u is sine x and du is cosine x, that makes u sub a really good way to simplify this expression. Okay, so now if I simplify, we get u to the power of 5 halves times du, and we are left over with this cosine x squared term. So there's a little bit left over. And we can't integrate this as is right now because of this over here. So we have to somehow get rid of that. And this is where we use the Pythagorean identity. So the Pythagorean identity states that sine squared x plus cosine squared x equals 1. Anytime we have, we're integrating trig functions, it's really important to remember all of those various different identities because they can be used to simplify our expression. So in this case, cosine squared x is equal to 1 minus sine squared x. So now what I can do here is I can take this cosine squared x and replace it with 1 minus sine squared x, and then we can use u sub. So after replacing it, sine x equals u, so I get u to the power of 5 halves times 1 minus u squared. Okay, and then if I expand this out, I get u to the power of 5 halves minus u to the power of 9 halves. Okay, and so now we can see the biggest benefit of u sub. We went from this complex expression to something that can be something which we can calculate the antiderivative of just using the power rule, the inverse power rule. So now, like I said, all we have to do to find the antiderivative of this is use the inverse power rule. So the antiderivative of u to the power of 5 halves is 2/7 times u to the power of 7 halves, and the antiderivative of u to the power of 9 halves is 2/11 times u to the power of 11 halves. And this is the antiderivative, and then plus c as our constant. Okay, and now the last step is to plug in sine. So if you notice, none of these answer choices here have u. That's because u is relative. We need to plug back in u equals sine x to get our correct answer. So after plugging it in, I get 2 over 7 times sine x to the power of 7 halves minus 2/11 times sine x to the power of 11 halves plus c. So that would make the correct answer for this problem D. Okay, moving on to question 2. Question 2 is a bit long. So question 2 says 3 students try to compute the antiderivative of tangent x, which is also equal to the antiderivative of sine x divided by cosine x. So Elijah's strategy is to use the substitution u equals sine of x. The integration then becomes, so let's walk through this. U equals sine x. That would make du equal cosine x. And so he plugs in u over here, and then it looks like he plugs in 1 minus u squared for the denominator. So, okay. So, yeah. So what he does is he rewrites this as sine x cosine x squared. That's not a good square. Times cosine x. Okay, and then after he does u sub, he plugs in u for the sine x in the numerator. He replaces this cosine x squared with 1 minus sine x squared. Again, this is because of the Pythagorean identity, which states that cosine squared x equals 1 minus sine squared x. So he uses the Pythagorean identity there to replace that, and that's how he gets 1 minus u squared in the denominator, and this cosine x becomes du. Okay, so that's what he does to get this expression, and then he separates this into partial fractions, which you can double check that his math is correct here, and then he uses the antiderivative rule for logs to find this answer over here. And so if you check his steps, the answer he calculates here is correct. This answer is correct because, yeah, I'm not going to go through it right now, but if you take the derivative of the answer he gets, you'll see that it matches what he has here. Okay. Mia goes a step further by taking this first u sub step and then doing one more substitution by saying v equals 1 minus u squared. That would make dv equal negative 2u. And so she plugs in v for the denominator here, and then negative 1/2 dv for u dv. So u du is equal to negative 1/2 dv. So that substitution is correct. Then she takes the antiderivative of negative 1 over v, and after resubstituting everything in, she gets this answer over here. And this is also correct. You can check that by taking the derivative of this expression. Okay, and then Santa doesn't do the substitution that Elijah did. Instead, he does w equals cosine x, and that would make dw equal negative sine x dx. So the expression becomes negative the integral of 1 over w dw, and that is equal to negative the natural log of w. And so he gets this answer over here. And this answer matches the typical formula for the antiderivative of tangent x. We know that this is like one of our basic antiderivatives. So from that knowledge, we can say that Santa is for sure correct. So Santa is for sure correct. Let's use a blue check mark. Santa is correct. Okay. So now we just need to determine whether Elijah and Mia are also correct. Because if we look at the answers, we can see that it says, so options A and B say only Elijah are right, only Elijah is right, and only Mia is right. And we know that is false because the formula for Santa is correct, and all his steps that he took to get that answer are also correct. Okay, so So C, D, and E say Santa is correct, but essentially all we have to do is figure out whether Elijah and Mia are correct. Okay, so the trick to this problem is knowing your trigonometric identities. So the important one I mentioned above is the Pythagorean identity. So typically we see the Pythagorean identity written as sine squared x plus cosine squared x equals 1. And this is very important. You should definitely have it memorized. So let's take a look at Mia's answer first. If you'll notice, Mia's answer has this 1 minus sine squared x term in it. And by the Pythagorean identity, this is equal to cosine squared x. Okay, and so that means that this is her answer is equal to this. And then the last step is that we need to know our natural log or our log rules. And you'll notice that they did it here in this final answer here. In Santa's answer over here. We have a negative in front of our log, but they take that negative away and cosine x becomes secant x. So this is because of the property of logs, which states that for a log n times the natural log of x, this is equal to the natural log of x to the power of n. So basically, if you have a coefficient in front of a logarithm, you can take that coefficient and make it the exponent for the argument. And I think it's also worth mentioning, do not get this mixed up with this. This is totally different. In this case, the exponent is acting on the entire natural log. This is not equivalent to these two statements. So make sure you don't mix that up. Okay, anyway, so by this property of natural logs, we can say that Mia's expression is equal to the natural log of cosine squared x to the power of negative 1/2. And cosine squared x to the power of negative 1/2 is equal to cosine x to the power of negative 1. And cosine x to the power of negative 1 is 1 over cosine x. So this is equal to the natural log of secant x. So ultimately, the answer that Mia calculated and the answer that Santa calculated are both equal. So Mia is also correct. Her answer just looks a little different because she did not simplify it. Okay, now moving on to Elijah's answer. Alright, so in this case, what I'm going to do first is I'm going to factor out this minus sign, and I'm going to bring out this minus sign and make this a plus and a plus, okay? Yep. So now we need to remember a second property of natural logs. When we are or not just natural logs, any logarithms, when we are adding two logarithms with the same base, so let's say natural log of a plus natural log of b, for example, that is equal to the natural log of a times b. So that's essentially what's going on here. We are adding, our first natural log is natural log of 1 minus sine x. The second is natural log of 1 plus sine x. So if we add those two together, I get negative 1/2 times natural log 1 minus sine x times 1 plus sine x. And if I expand that out, I get 1 minus sine squared x. And you'll notice, and there should be an absolute value here, you'll notice that that is exactly the same as what Mia initially got. this result is exactly the same as this. And that means that Elijah's result is equal to Mia's result, which is equal to Santa's result. So all three answers are correct, making the answer to this problem D. So the trick in this problem was to realize that all three of the answers that Elijah, Mia, and Santa got are equivalent due to trigonometric identities and natural and logarithm rules. But if you either forgot the identities, or maybe you didn't remember the natural log, how to add logarithms, you could have also walked through each step of the antiderivative process that Elijah, Mia, and Santa each did to determine that, yes, each process is correct. So whether the expressions look similar or not, since the process was correct, that would make the answer, all three answers, equivalent. Okay. Moving on to question 3. So question 3 says, compute the integral from 0 to 2 pi of sine squared x times cosine squared x. Alright, so one option when we see an expression containing sine and cosine is to use use substitution and set u equal to either sine x or cosine x. And so what happens is we set u equal to, suppose, sine x. We could also, and then that would make du equal to cosine x. This is a great option because this expression over here consists only of sines and cosines. So u sub can really simplify that expression. However, in this case, we have a second option that relates to another strategy that we can use anytime we have trig functions. Anytime we have trig functions, it's a good idea to consider if there are any trig identities that we can use. And so trig identities are mainly the Pythagorean identity, which states, so it's worth writing down. The Pythagorean identity states that sine squared plus cosine squared is equal to 1. And then the others are the double angle identity. So this cosine 2a is equal to cosine squared a minus sine squared a. And sine 2 alpha equals 2 sine alpha times cosine alpha. So if you'll notice, this last identity, the right-hand side, looks very similar to what we have over here. So in this problem, the best strategy is to use the double angle identity for sine of 2a to simplify this expression over here. So we want to use this expression over here. Sine 2a is equal to sine of 2 alpha is equal to 2 times sine alpha times cosine alpha. Okay, so by the double angle identity, this expression is equal to sine of 2x divided by 2 squared. Okay, then so now we get, I'm going to pull out this 1/4 because that's a constant. Now we have sine squared 2x. Okay, so now we have another problem because this is not something that we can just use one of our basic antiderivative rules on. So what do? The good thing is we can use our other double angle identity. So there are two other forms for the cosine double angle identity, and we get them by using the Pythagorean identity and substituting in Either we substitute in 1 minus sine squared for this cosine squared, or we substitute 1 minus cosine squared for this sine squared. But cosine of 2 alpha is also equal to 2 times cosine squared alpha minus 1, or 1 minus 2 sine squared alpha. So all 4 of these statements, so cosine 2 alpha, cosine squared alpha minus sine squared alpha, 2 cosine squared alpha minus 1, and 1 minus 2 sine squared alpha 1 minus 2 times sine squared alpha, all 4 of those statements are equal, which is very convenient for us. And the identity we want to use in this case is the identity that relates sine squared alpha to cosine 2 alpha. So I'm gonna write this out down here. So if I rearrange, I can solve and find that sine squared alpha is equal to 1 minus cosine 2 alpha divided by 2. Okay, and so now if I use this on the expression that I have in my integral, I get 1 minus cosine 4x divided by 2. Okay, and it's very important that you remember to change this 2x to a 4x. Even though our identity states that alpha is equal to sine squared alpha is equal to 1 minus cosine 2 alpha divided by 2, you have to understand that in this case, alpha is equal to 2x. So don't make silly arithmetic mistakes, basically. Okay, and then I'm going to factor out the 1/2 to get 1/8 as my constant in front. Okay, and then I'm left with this. And now our integral has simplified into something that I can just use basic antiderivative rules on. This 1, the antiderivative of 1 would be x. And the antiderivative of cosine 4x is sine 4x divided by 4. Okay, and we evaluate this antiderivative from 2 pi to 0. So now I just plug in my bounds. I get 2 pi minus the sine of 8 pi would be 0. And then subtract 0 minus, the sine of 0 is also 0. So this is equal to pi over 4, meaning the answer to problem 3 is E. Okay, moving on to problem 4. Okay. Problem 4 asks, compute the integral of tangent x to the power of 4 times secant x to the power of 4. So this question is another problem where u sub is a really good choice. So we also see a similar type of question, which is sine, powers of sine and cosine. And in that case, we can use u sub. So u sub is where we set u equal to some function, and we essentially do a change of variable on our original expression. And essentially by changing this variable, we turn the original tricky expression into something that is a lot easier to find and calculate the antiderivative of. So u sub is a really great option when you can see that the original expression consists of a function and the derivative of that function. So in this case, our function that we use for substitution would be tangent x. And the derivative of tangent x is secant squared x times dx. So with u sub, essentially what you do, like I did here, is you set u equal to some function. You also have to calculate du, and now we can replace our original expression with these two elements, and hopefully that will simplify our problem. So if I plug this in, I get u to the power of 4 times secant squared x times du. Okay, so we plugged things in, but we are still left with one problem. We still have a x term, a function of x, in our expression. If we want to do u sub, everything has to be in terms of u. So somehow we need to get rid of this secant x squared. So the way we can do this is by using trig identities. Anytime we have an expression that consists of various trig identities, what we want to do is consider your trig identities that can be used to simplify trig expressions within integrals. So in this case, I think arguably the most important trig identity to remember is the Pythagorean identity. So you might be familiar with the Pythagorean identity as in this form, which states that sine squared x plus cosine squared x equals 1. However, there are also like two other variants that we can get, basically by dividing this expression by either sine squared x or cosine squared x. So you'll see that if I divide this expression by cosine squared x, I get tangent squared x plus 1 is equal to secant squared x. So, and then likewise, if I were to divide by sine squared x, I would get 1 plus cotangent squared x equals cosecant squared x. So as long as you remember this first identity here, you can always derive the other two. So the reason this is useful, though, is I have this second statement says that secant squared x, which we have in our expression here, is equal to tangent squared x plus 1. So that means I can rewrite this as u to the power of 4 times tangent squared x plus 1. Oops. And now we can use u sub and replace the tangent x squared with u squared. Okay, so I get u to the power of 4 times u squared plus 1 du. And let me rewrite this in blue. So, okay. And then now if I expand this, I get u to the power of 6 plus u to the power of 4 du. And now you'll notice that this original expression that we have, which was tricky, and we have no like good way to find the antiderivative, this is reduced into an expression which we can just use our basic antiderivative rules. So in this case, we would use the power rule. Okay, so by the power rule, the antiderivative of u to the power of 6 is 1/7 times u to the power of 7, and the antiderivative of u to the power of 4 is 1/5 times u to the power of 5. And the last step with u sub is to go back and plug in the original expression that is in terms of x. So we need to plug in tangent of x back into u. And if I do that, I get 1/7 times tangent x to the power of 7 plus 1/5 times tangent x to the power of 5, and this is plus c. So I forgot the plus c here, but yeah, plus c. Okay, so that would make the correct answer to problem 4, C. Okay, moving on to problem 5. Problem 5 states, compute the integral of tangent x times secant x cubed. Okay, so this is another problem which consists of two trig functions being multiplied. So we either see sine of x times cosine of x, or we see tangent x times secant. And anytime we see integrals in either of those two forms, a really good option, not always, but most of the times, a really good option is u sub. And so the reason is, well, let's start off with explaining what u sub is again. U sub is when we set a function of x, when we set a function of x equal to some arbitrary variable u. So like for example, I could set u equal to tangent x, and du in that case would equal secant squared x times times dx. And what u sub allows us to do, it allows us to do a kind of change of variable on our original expression, and that can help us simplify our original expression, which makes it easier to find an antiderivative for our expression. Okay, so in this case, I gave an example, u equals tangent x, du equals secant squared x. The reason u sub is a good opportunity, a good strategy in this specific problem is because we have both tangent x and secant x. U sub is always a good option when you see that the expression has a function and the derivative of that function, something that looks similar to the derivative of that function. So I have tangent x, the derivative of tangent x is secant squared x. So that's how I get the idea that maybe u sub is a good choice to use here. Alright, so now we have to actually execute this u sub. So I have 0 and then pi to 4. I plug in u for tangent of x, and then du for secant x squared, and I am still left over with secant x. Okay, so this is a problem because to actually use u sub, everything in this expression has to be in terms of u. So I can't have some stuff that is in terms of u and then just this one leftover x term. Everything has to be in terms of u. So one strategy that we can use, since we are dealing with trig functions, I can try and use trig identities to simplify, to get rid of this secant x. So the most important trig identity to remember is the Pythagorean identity, which states that sine squared x plus cosine squared x equals 1. This is your main trig identity. You can derive the other two by dividing either by sine squared or by cosine squared. So if I divide by sine squared, I get 1 plus cosecant squared x equals 1. Oh, not 1. It equals okay. Let me start over. If I divide by sine squared x, I get 1 plus cotangent x squared equals cosecant x squared. And then if I divide by cosine squared x, I get tangent x squared plus 1 is equal to secant x squared. So by the third equation that I wrote down here, this secant x would equal the square root of u squared plus 1. Because secant squared x is equal to tangent squared x plus 1, and we said that u is equal to tangent x. And that means that this would be our new u sub expression. Okay, so the problem here is that doing u sub didn't actually simplify anything. This is probably just as difficult to compute as the original integral. And actually, I think we could do another u sub and solve it, but know that this is something that does happen sometimes. Sometimes we try u sub and it doesn't work. The good thing here is that we set u equal to tangent x. We have another option though. The other option is to set u equal to secant x. And so when u sub doesn't work out initially, I would suggest trying other similar options if there are any, because sometimes the first option you pick might not always work. So if I set u equal to secant x, du would equal tangent x secant x dx. And you'll notice this secant x is still a good choice because the derivative of secant x is in terms of tangent x and secant x, and tangent x is also in our original expression. So yeah. Okay. Now with this new u sub, if I plug things in, I get I get u squared times du. Alright, and you'll see, yes, this second u sub worked perfectly. Now I have something that is actually easy to find the antiderivative of. Okay, and the last step is to figure out the lower and upper bounds. So the lower and upper bounds that we have here are 0 and pi over 4. But since this integral is in terms of x, we're doing dx. That's like saying the lower bound is x equals 0 and x equals pi over 4. Now that we're integrating in terms of du, I can't use these same lower and upper bounds. I need to calculate those bounds in terms of u. And the way I'm going to do this is by plugging in the lower and upper bounds into this equation over here. So to find the lower bound, we take secant of 0. That's equal to 1 over cosine 0, which is equal to 1. So the lower bound is 1. Do the same thing for the upper bound. We take secant of pi over 4, which is equal to 1 over cosine pi over 4, which is equal to 1 over root 2 over 2. So the upper bound is equal to root 2. Alright, and now we can just take the antiderivative as normal. The antiderivative of u squared by the power rule is u cubed over 3. And we're going to find that from 1 to root 2. So that's equal to root 2 cubed over 3 minus 1 cubed over 3. And if I simplify that, I get 2 root 2 minus 1 over 3 as my final answer. So the answer to problem 5 is C. Okay, moving on to question 6. Okay. Question 6 says we try to compute the integral of tangent squared x times secant x dx using integration by parts, setting u equal to tangent x and v equal to secant x. And then du would equal secant x squared, dv would equal secant x times tangent x. And then they end up doing all of this math, and ultimately they find that the integral of the antiderivative of tangent x squared times secant x is equal to tangent x times secant x minus tangent x squared times secant x. Okay, so of the options available, maybe before we look at the answer choices, let's try to see if we can simplify this answer that we're given. So the first thing we can notice is that this integral here on the left-hand side is equal to this integral here on the right-hand side. So basically, I can move this over to the right-hand side, and I get 2 times the integral of tangent squared x times secant x is equal to tangent x times secant x. I'm going to move this to a different line. Minus the integral of secant x. And then if I divide both sides by 1/2, I get that this integral over here is equal to 1/2 times tangent x times secant x minus 1/2 of the antiderivative of secant x. Okay, so basically we do have a formula for the integral in question, for the original integral that we are trying to compute. Yeah, so that's important, recognizing that this and this are the same, and moving this minus tangent x squared times secant x term to the left-hand side, that is very important. The second part of this problem is to see if we can calculate this value over here, the antiderivative of secant of x. So in order to do this, you just have to remember the formula for the antiderivative of secant. It's a bit difficult to remember, so it might take a bit of practice. But the antiderivative of secant of x is the natural log of tangent x plus secant x. And so our final expression for the integral in question is 1/2 times tangent x times secant x minus 1/2 times natural log of tangent x plus secant x. So in that case, the correct answer, oh, and then we can't forget this, but all of that plus c are constant. So that means that the correct answer for this problem is D. Okay, and I think it's also worth going through why the other problems are not correct, why the other answer choices are not correct. So we can go through each one now. So statement A says, since we end up seeing the same formula at the end, they're talking about this term here that I underlined, the tangent squared x times secant x. They say that because we have that same term at the end, this trial fails to compute the integral. That is false, because like I showed, we can add this integral to both sides and use that to still solve for the value of that integral. So that's why statement A is false. So statement B says the only substitution we can use is u equals tangent x or u equals secant x. For the given integral, neither of them works. The above trial confirms that this integral cannot be computed by any method. Okay, so that is false because we were able to calculate the value of the expression. Okay, statement C gives a formula, and it is very similar to the one we calculated, except they forgot the 1/2. So statement C is due to an arithmetic error. So it's important to remember that you have two of these expressions. So that's why we have the 1/2 in front. Okay, and then statement E says the above trial fails. We have to use the formula tangent squared x is equal to, they use a substitution they say that tangent squared x is equal to secant squared x minus 1. That's the Pythagorean identity. However, using... Okay, so they use this... Okay, yeah, the key word here is only. So this, what they do is a valid method. However, again, we did calculate the right answer, so that means that E is also false, because this is not the only way we can calculate this integral. So yes, that is why D is the correct answer. Okay, problem 7 says, evaluate the integral from 0 to 5 over root 2 of x squared divided by the square root of 25 minus x squared. Okay, so anytime we have the square root of a constant minus some term squared, a really good option to use is trig substitution. So trig substitution is when we set our variable x equal to some trig function. And we can see why this is the case by looking at the Pythagorean identity. So the Pythagorean identity states that sine squared theta plus cosine squared theta equals 1. And then there are two other corollaries, I guess, which state that 1 plus tangent squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. The only important one to remember is this first one. You can derive the second and third ones by dividing this first equation by cosine squared theta and sine squared theta respectively. Okay, and actually I'm going to rewrite this first equation as 1 minus cosine squared theta equals sine squared theta. So, like I said, these identities are the reason why trig sub is a good choice when we have a term like this, like the square root of some constant plus or minus c. Okay, so instead of, there's a way to pick what value to substitute for x, but I'm going to go through kind of derivation to show you like how you could decide which one to choose without memorizing. So what I'm going to do first is I'm going to pull out this 5 from the radical. That leaves 1 minus x over 5 squared underneath the radical. And now I want to make this expression inside the radical either look something like 1 plus tangent squared theta or 1 minus cosine squared theta. You'll see that I have a minus sign here, so this expression has to equal 1 minus cosine squared theta, which means x would equal 5 cosine theta. So this is going to be the expression that allows us to simplify the radical. Okay, so now if x equals 5 times cosine theta, I also have to calculate dx. dx would equal negative 5 sine theta. And now I just plug these values into the expression. So I get 25 cosine theta squared, 5 times 1 minus cosine theta squared under the radical times negative 5 sine theta. Now this over here, this will simplify to sine theta. The whole, I'll put a square. That will all simplify to sine theta. And so ultimately this will simplify to 25 times cosine squared theta, d theta, negative 25. Okay, so we've already simplified our expression a good deal. However, cosine theta squared, that's not something that we can easily find the antiderivative of. So we actually need to use another trig identity to simplify this. And in this case, the trig identity to use when we either have cosine squared or sine squared is the double angle identity for cosine. So the double angle identity states that cosine 2 theta equals cosine squared theta minus sine squared theta. And this is also equivalent to 2 times cosine squared theta minus 1, which is also equivalent to 1 minus 2 sine squared theta. So our last two statements relate cosine 2 theta and cosine theta squared and sine theta squared. So in this case, we want to use the fact that cosine 2 theta equals 2 cosine squared theta minus 1. And so if I use that identity, I get negative 25 halves cosine 2 theta plus 1. So this expression here is equal to this, using the double angle identity for cosine 2 theta. Yep. Okay, and now we have something that we can easily calculate the antiderivative of. Okay. All right. And so let's find the antiderivative. I can pull the negative 25 halves out. The antiderivative of cosine 2 theta would be sine 2 theta divided by 2. And the antiderivative of 1 is just theta. But you'll see that this whole time I still don't have my lower and upper bounds. So you might be tempted to use 0 and 5 divided by root 2. However, you have to remember that these lower and upper bounds are in terms of x, and we are integrating in terms of theta. So we actually need to use this original equation over here and solve for our new lower and upper bounds that are with respect to theta. And the way we do this is first I'm going to write theta in terms of x. So theta is equal to the arc cosine of x over 5. And now I plug in these two values into this equation. So if I plug in 0, I get my lower bound to be pi over 2. And if I plug in 5 divided by root 2, I get my lower bound to be pi over 4. Because the arc sine of 0 would be pi over 2, because that's where cosine is 0. And the arc sine of 1 divided by root 2 is pi over 4, because at pi over 4, cosine is root 2 over 2. Okay, and then now I can just plug things in and find the answer. Okay, so negative 25 halves. The sine of 2 times pi over 4 is 1/2. Well, 1, so I get 1/2 plus pi over 4 minus 0, because sine of 2 times pi over 2 is 0, minus pi over 2. And that is equal to negative 25 fourths plus 25 eighths pi. So the correct answer would be A. Alright, moving on to problem 8. Okay, problem 8 says, compute the integral of the square root of x squared minus 49 divided by 7x with the condition x is greater than 7. Okay, so for this problem, you'll notice that we have the square root of something squared, a variable squared minus 49. This is a pretty good indication that we want to use trig sub for this question. Trig sub is where we set our variable, our integrating variable x, equal to some trig function. Alright. And the reason we do this is due to the Pythagorean identities, which state that sine squared theta plus cosine squared theta equals 1. And then we also, from these identities, can find the two identities 1 plus cotangent squared theta equals cosecant squared theta, and 1 plus tangent squared theta equals secant squared theta. You only need to memorize this first identity, which is really important. You should memorize it. You can derive these two by dividing the first equation by dividing the first equation by sine squared theta and cosine squared theta, respectively. Okay, so yeah. And I'm going to actually rewrite this first equation as 1 minus cosine squared theta equals sine squared theta. Essentially, what we want to do using trig sub is substitute x with something so that our equation, our value under the radical is something like this. And then since this is equal to like another trig function squared, the entire radical simplifies to just one expression. Okay. It's not always obvious as to which substitution we should use, but luckily there's a way we can derive this. So what I can start by doing is factoring out this constant. So I'm going to factor out the 49 from the radical. That gives me 7. Oops. So I'll factor out 7, and then I get square root of x over 7 squared minus 1. And the 7 in the numerator cancels with the 7 in the denominator. Okay, so now I want this to equal one of these expressions. Okay, well, I have a minus 1 here, and all of these expressions have a plus 1. So first step would be to subtract 1 from each of these expressions. So if I subtract 1 from this equation, I get tangent squared theta equals secant squared theta minus 1. And I get negative cosine squared theta is equal to sine squared theta minus 1. Okay, and the reason I'm not doing this identity over here is because this identity and this identity, so the second and third identity that I wrote here are actually like very similar. So kind of for the purposes of trig substitution, we only have to worry about the 1 plus tangent squared equals secant squared identity and the sine squared plus cosine squared. Usually, we can either use sine, tangent, or secant as our substitution. Doing a secant substitution is essentially the same as doing a cosecant, and doing a tangent substitution is the same as doing a cotangent, except doing cotangent and cosecant is just more hard. Because, yeah. Okay. It's more hard because they essentially work the same way, except you have negatives. So cotangent, the derivative of cotangent theta is negative cosecant squared theta. That can be the signs can be a little annoying to work with. Okay. Anyway, so I have these two expressions now. And you'll see that I should set x over 7 equal to secant theta. The reason it's not sine theta is because if I did set x over 7 equal to sine theta, the expression under the integral would become negative cosine squared theta, and we can't take the square root of a negative value. So what we're going to do is we're going to set x equal to secant theta. Not secant theta, sorry. X is equal to 7 times secant theta. By setting x equal to 7 times secant theta, this expression equals this expression, and I will be able to simplify this radical since everything under the radical will evaluate to tangent theta squared. Okay. And then now that I have x equals 7 times secant theta, I can also write dx is equal to 7 times tangent theta secant theta. Okay, now we just substitute as normal. I get secant squared theta minus 1 in the numerator, 7 times secant theta in the denominator, 7 times tangent theta times secant theta times d theta. Okay, the 7 secant theta cancels out, and by the Pythagorean identity, the secant squared theta minus 1, radical of secant squared theta minus 1 will equal tangent squared theta. So ultimately, this integral equals tangent squared theta d theta. Okay, however, there's no integral for the tangent squared of theta. So what I can actually do is I can rewrite this, again, using the Pythagorean identity. I can rewrite the tangent squared theta as secant squared theta minus 1. So this is a general theme for any problem involving trig functions. When you can't integrate the trig function, it's always good to do substitutions to try to put the function into a form that is easier to be integrated. In this case, we know the antiderivative of secant squared theta, and we know the antiderivative of 1. The antiderivative of secant squared theta is tangent theta, and the antiderivative of negative 1 is theta. So we have an expression for the antiderivative. The only problem, the last thing to do, is to rewrite this in terms of x. And to do that, we need to use the equation from the start. All right. So I can rewrite it down here. X is equal to 7 times secant theta. All right. Tangent theta is equal to, again by the Pythagorean identity, 1 minus secant theta squared. So in terms of x, it's equal to 1 minus x squared over 49. And I can multiply both the top and bottom by 7. So I get 1/7. So if I multiply like 7 times 7, I can send this top 7 inside the integral, and I get 49 minus x squared. So tangent theta is equal to 49 minus x squared. And if you still can't see, it might make more sense. I can multiply the top by root 49 and the bottom by 7, and that's how I get this value for tangent theta. Okay, and it's a little easier to solve for theta. Theta is equal to the arc secant of x over 7. So that means that this is equal to 1/7 times the square root of 49 minus x squared minus the arc secant of x over 7. And can't forget the plus c. So our answer to problem 8 is A. Okay, moving on to the next problem. Problem 9 says, choose the appropriate trigonometric substitution to compute the integral of square root of 7 plus 12x plus 4x squared. Okay, so usually when we use trig substitutions, we're given something that's way simpler. Like, it's usually a constant minus x squared or a constant plus x squared. We don't always, it's rarer to get a whole polynomial like this. Okay. And I think first let's go over what a trig substitution again. A trig substitution is when we set x equal to some trig function. And usually it's either sine theta, cosine theta, and doing sine theta and cosine theta is like the same. you'll end up walking through like an almost identical process. So sine theta or cosine theta, tangent theta or secant theta. And the reason we use trig substitution most often in cases when we have the square root of a variable squared plus or minus a constant. Okay, and the reason is because of the trig identities, this is one trig identity, and the other relevant trig identity is 1 plus tangent squared theta equals secant squared theta. And I'm actually going to rewrite this first one as, usually when we do trig sub, it's more helpful to rewrite this first identity as sine 1 minus cosine squared theta is equal to sine squared theta. Okay. And this last identity, we can also rewrite it as secant squared theta minus 1 equals tangent squared theta. Alright, so the trick here when we're given a more complicated expression and we want to use trig sub is to complete the square, because we want to get it into a form where we have a constant. So in all of three of these like examples that I've shown, we have a constant plus our trig term. So essentially we're going to complete the square and put it into a form where it's a constant plus our variable terms. Okay, so I'm going to complete the square for this. And the way I complete the square is by doing 2x. So this first term is 4x squared, right? So the square root of 4x squared is 2x. So that's why we have 2x. The constant term, the way we calculate the constant term that goes here is we find the coefficient in front of the x term. We divide it by 2. So we divide by 2 to get 6. And then we divide that by the coefficient of this term. It's also this, we divide by the square root of the a term in our polynomial. In this case, the a term is 4, the square root of 4 is 2, so I end up with 3. So 3 is a number that goes here. So if I factor this out, I get 4x squared plus 12x plus 9. And to complete this square, I have to essentially subtract just enough so that I get this. And I have a 9 here when it should be a 7, so I want to subtract 2. So ultimately, I'll write it in a different color. Oops. I get 7 plus 12x plus 4x squared is equal to 2x plus 3. 2x plus 3 squared minus 2. Okay. And now I'm going to go back up to the integral and I'm going to rewrite this as such. 2x plus 3 squared minus 2. Okay. And now what I'm going to do, whenever I'm trying to figure out which trig subs to do, the first thing I do is I factor out the value of this constant. The reason is because if you see in all of these equations, I have a 1. So factoring it out helps me see much better like which one I should use. So if I factor this out, I get root 2 times 2x plus 3 divided by root 2 squared minus 1. Okay. So now I have to see which of our equations looks most similar to this. Well, it's obviously not 1 minus cosine squared theta because the squared term here is being added. It's not being subtracted. So it's not this one. Okay. Is it 1 plus tangent squared theta? No, because I have a plus 1 here and I have a minus 1 here. So that means that I want this expression to equal secant squared theta minus 1. So secant squared theta minus 1 should equal 2x plus 3 squared, oh, that's weird, divided by root 2 minus 1. So that's how I go through that process. Now I can cancel this negative 1 here, and we can also take the square root of both sides. So I get secant theta is equal to 2x plus 3 divided by root 2. And if I multiply both sides by 2, I get 2x plus 3 equals root 2 times secant theta. So that means that the correct answer to problem 9 is E. Alright, moving on to the next question. Okay, questions 10 says, write out the form of the partial fraction decomposition of the function 1 divided by x minus 2 squared times x squared minus 4 times x squared plus 4. And the important thing to note here is that they don't want us to actually find the partial fraction decomposition. They just want us to find the general form. Okay, so the first thing we should do is double check the denominator to make sure everything is completely factored. So you'll notice that the second term is not completely factored. X squared minus 4 equals x plus 2 times x minus 2. And I can rewrite this, therefore, as 1 divided by x minus 2 cubed times x plus 2 times x squared plus 4. Okay. So we can go term by term and discuss what partial fractions are necessary. So for this x minus 2 cubed term, I'm going to need 1 over x minus 2 up to x minus 2 cubed. So I need 1 over x minus 2 squared as well, plus 1 over x minus 2 cubed. I need each of those. Okay. For x plus 2, since I only have x plus 2 to the power of 1, that is enough. I just need 1 over x plus 2. And now I have x squared plus 4. And since x squared plus 4 has a multiplicity of 1, I only need one fraction with x squared plus 4. However, unlike the others, I have x squared plus 4 here. So the numerator, since the other, okay, so for the other like factors in the denominator, they are polynomials of degree 1. So the numerator of each of those fractions only has to be a constant. However, since the degree of this polynomial is 2, the degree of the polynomial in the numerator has to be of degree 1, which would be in the form like mx plus n. So basically x plus a constant. So according to what we have found here, oh, and I wrote 1 over x minus 2 here, but technically they would each need to be constants. Don't get that confused. So since we have a polynomial of degree 1 in the parentheses here, we can have a polynomial of degree 0 in the numerator at most. So a polynomial of degree 0 is a constant. So that's why we have a constant here. And likewise for each of the 3 other partial fractions. It doesn't matter that we have x minus 2 squared. All that matters is what's in this parentheses, which is a degree 1 polynomial. Okay, so according to what we have found here, the correct answer would be E, because we have x minus 2, x minus 2 squared, and x minus 2 cubed, x plus 2, and x squared plus 4. And for each of the numerators, we have a constant, and a degree 1 polynomial. So the correct answer for 10 is E. Okay, moving on to problem 11. Problem 11 says, evaluate the integral x squared plus 6x plus 17 divided by x times x squared plus 8x plus 17. So anytime we have the ratio of two polynomials, that is a pretty good indication that we should use partial fraction decomposition to find the antiderivative. Another big clue to notice is that they, for some reason, factor the denominator. So the fact that they factored this denominator is like a subtle clue that it might be a good idea to use partial fraction decomposition. So if I use partial fraction decomposition, I could have x squared plus 8x plus 17, and the only difference between this polynomial and this polynomial is a 2x. So I could put a 1 up here and a 2 over here. And that's how this is the equivalent expression for this. Okay. If you need it also, if that's not immediately obvious, you can also use algebra to solve for A, B, and C in this case. So, and I'd put a plus here. So ax squared plus 8ax plus 17a is equal to, plus bx squared plus cx is equal to x squared plus 6x plus 17. I'll say it again, but A, B, and C are all constants. That's important. Okay, and then now I'm going to group things in this left-hand side of the equation based on term. So if I group everything up for 8x squared, I get A plus B. If I group everything up for x, I get 8a plus c, and then I get plus 17a. Okay, so that means a plus b equals 1. A plus b equals 1. A plus c, 8a plus c equals 6, and 17a equals 17. So from that last equation we get a equals 1, which we can use to solve b equals 0. And 8a, okay, and then c would equal -2. Alright, and so that's how we get, that's a more like rigorous way of showing that the expression in the integral is equal to 1 over x plus, minus 2 over x squared plus 8x plus 17. Okay, so we can evaluate these two parts of the equation separately. So if I evaluate this first part, I get natural log of x. Okay, and so all we have left now is to evaluate this -2 over x squared plus 8x plus 17. Okay, so there are two ways to do this. Let's try to see if we can factor this anymore. It should be pretty obvious that we can't factor this anymore because the 17 is a prime number, so 17 can only be factored by 1 and 7, and x plus 1 times x plus 17 is not equivalent. It's not equivalent to that polynomial. So we can't use partial fractions again. What we can use is we can use tangent, arctangent. So let me write it in a different color. The derivative of arctangent is equal to 1 divided by x squared plus 1. So we have a 1 up here, and we do have an x squared. It's not quite the same, but maybe there's a way we can make this look similar enough so that somehow we can relate this to the derivative of arctangent. And the way we're going to do this is by completing the square of the polynomial in the denominator. Okay. So if I complete this square, I get 1 divided by x plus 4 squared plus 1. So the way I typically complete the square is I take the square root of the first term. That's going to be the first number that goes in our parentheses. And then I take the second term, divide it by 2, and then I divide it by the coefficient of the first term. Okay, so I have x plus 4 squared plus 1. Okay, and you'll see that this looks very similar to 1 over x squared plus 1. Instead of x squared, I have x plus 4 squared. So we can use u sub. U sub is where we set some variable equal to u. Where we set u, which is some arbitrary variable, equal to a function of x to simplify our expression. So if I set u equal to x plus 4, du is equal to 1. Du is equal to dx. And this would equal natural log of x minus 2 times 1 over u squared plus 1 du, which is equal to natural log of x minus 2 arctan of u. And now I can just plug in x plus 4 back for u, and I get natural log of x minus 2 times arctan of x plus 4. So that is our final, plus c. That is our final answer. So the correct answer in this case would be C. Alright, moving on to problem 12. Okay, problem 12 says evaluate the improper integral from 0 to infinity of x times e to the power of negative 5x squared times dx. Okay, so the first step here is calculating, the first step here is let's get rid of this infinity. Technically, we're not allowed to integrate to an infinite number, so what we do instead is we integrate from 0 to b, and we say, what's the limit as b approaches infinity? Okay, so now we've taken care of this improper infinite bound. Now we have to take a look at the expression in our integral. The expression is x times e to the power of negative 5x squared. This is not something that we can easily find the antiderivative of, so we have to use one of our integration methods. And in this case, the method we're going to want to use is u sub. So u sub is when we set u, which is some arbitrary variable, equal to a function of x. And u sub is a good choice when we see that within the function that we are trying to find the antiderivative of, there's some function, and then like what looks similar to the derivative of that function. So in this case, I have negative 5x squared, which I can set as my u, and du in that case would equal negative 10x. And you'll notice in front of the e, I have an x, which is very similar to negative 10 times x. They only differ because I'm multiplying by negative 10 here. So that's why we would use substitution in this case. Okay. So we use substitution, and then, okay, now this is du equals negative 10x times dx. Okay. So after using substitution, this expression simplifies to negative 1/10 times e to the power of u du. And now I just have a constant times e to the power of u. That's very easy to find the antiderivative of. The antiderivative is simply, it's simply e to the power of u. And you'll notice that I didn't write in my lower and upper bounds yet. The reason is because these lower and upper bounds are with respect to x. Right now I am integrating with respect to u, so I'm not going to write in the bounds yet. I'm going to convert back to x before I write down my bounds. So the way I convert back to being in terms of x is I just use this equation again. I have e to the power of negative 5x squared. Okay, and this is from 0 to b. So if I evaluate this, I get negative 1/10, and I'm actually going to pull this negative 1/10 all the way out of the limit. Negative 1/10 is a constant, which is why we can pull it all the way out. It's not being affected by the value of b. Okay, I get e to the power of negative 5b squared minus e to the power of 0, which is 1. Okay. And yeah, okay. So now I just have to find the limit of this term as b approaches infinity. Well, as b grows larger, negative 5b squared approaches infinity. So we can kind of instead ask, as b grows larger, negative 5b squared approaches negative infinity. So instead, I can ask, as n approaches negative infinity, what is the behavior of e to the power of negative n? Well, e to the power of n. Let's be careful. Well, we can draw a graph of e to the power of n, and it's going to look like this. And as n gets smaller and smaller and smaller, it's going to approach 0. So the answer to this is 0. So that means that the limit as b approaches infinity of this term is 0 as well. So I have negative 1/10 times 0 minus 1, which evaluates to 1/10. So the answer to problem 12 is 1/10.